All right, let's get started with 4.2. Here we're talking about the mean value theorem and using some of its consequences when we're trying to figure out what graphs may look like or what properties functions may have. So first we're going to ask a couple questions that we're going to answer later on as we go through this based on what we learn here. And so one, we know that any constant function has a derivative of 0, but could there be a more complicated function whose derivative is always 0? And so you may have an intuition on that one, but we want to be able to, say it definitively. And two, if two functions have identical derivatives over an interval, how are the functions related? All right, so let's look at Rolle's theorem. Suppose that y equals f of x is continuous at every point of the closed interval a to b, and differentiable at every point of its interior. So first, paying attention here, we have a closed interval a to b. It's differentiable at every point in that interval, and it's continuous at every point of that interval. All right, so we need those two things. If the beginning of the interval, the function plugged in, f of a, is equal to the same output value at the end of the function, f of b, then there is at least one number, and we'll call it c, in AB, in that interval, for which we're going to have a derivative value equal to 0. In other words, we are going to have a tangent function, a tangent line that is 0 at least one point. And so to see that, let's take a look at these two graphs here. Here we have this blue upside down parabola looking graph, and you can see that it is smooth, it is continuous, it has no breaks in it, it's differentiable at every point. There's no sharp curves or any sharp points or anything like that. It doesn't jump anywhere. And so if we start at a, f of a, and we end at f of b, and they both have the same value, in other words, we draw a horizontal line and it hits the graph at those 2 points, then somewhere between where that horizontal line hits the graph, where those two values are the same, you're going to have at least one point where the tangent line is 0, where the derivative function is 0, and therefore the slope of the tangent line is 0. Because if you think about this, if you start drawing at A, there's nothing you can do, no matter what. If you want to get back down here to B, at some point, you're gonna have to make that arch over and get that tangent line that's gonna equal 0, because you're gonna have to go back down if you started going up. And the same thing, if you had started going down, eventually you're gonna have to do something to turn back up, and you're gonna have that tangent line 0. And if you don't see that immediately, then go and draw a picture. Draw 2 points that are horizontal with each other like this. Try to connect them together without ever at least one point having a horizontal slope, without ever, no lifting your pen, no doing sharp corners. Draw a smooth continuous function. Even if you just draw a straight line, well, then you have at least one point. Every point on there is a slope of 0. But try to do whatever you can. You can't do it, and you may end up putting lots of horizontal tangent lines that are equal to 0. Okay, so give it a try. You'll see that you can't do it. No lifting your pencil, no sharp corners. And then take a look at this next graph. You can see here. So when we say at least one, here are multiple. Again, we have this point and this point having the same output value. So in other words, they're connected by a horizontal line. Then that means that we have to have at least one. And you can have numerous ones. There's one, there's one, there's one, that are all horizontal tangent lines where the derivative equals 0. All right, so assuming the conditions above, a horizontal, I don't know how to put this, line connecting 2 points on the graph implies at least one horizontal tangent between the 2 points. All right, I'm not going to write all that in. It's getting a little crazy. And so here are some examples where we see that it is not going to have a slope or a tangent that is equal to 0 at any point, or tangent that has a slope of 0 at anywhere in the point. So here we're connecting 2 points with that horizontal line, but it's discontinuous. It's discontinuous there. And since that is the case, we have no place on there that's a tangent line. Here, and that's discontinuous at an endpoint. Here it's discontinuous at an interior point, right? Interior point. And again, that also can make it so that we'd have no horizontal line. Like everywhere you try to draw a tangent line, it's not going to be 0 sloped. Okay? And then the last one, this one is continuous, but it is not differentiable at an interior point. And that's at that point right there. And again, we have no slope at that sharp corner, and so we can't do it. So if we don't have those two things, if we don't have smooth and continuous and differentiable at every point in the interval, then we may not have a zero slope tangent line in it. Okay? So let's take a look here. The mean value theorem. The mean or average value theorem is a generalization of Rolle's theorem. And so what this basically does is it says that if you suppose f of x is continuous on a closed interval AB and differentiable in the interior AB, then there is at least one point C in AB where this is the case. All right? And so what this is saying is now, before where we said we had at least one point where we had a 0, what we're saying is, if we look at this picture over here, if we're looking from the point A, B in this closed interval, if we connect them with a straight line, right? If we connect them with a straight line, that straight line will have a slope. And no matter how we go about trying to draw this and connecting them together, there is going to be at least one point that has a tangent line that is parallel to that. And in fact, there can be more, like in the way I just drew it compared to what the picture there that was given. But there's going to be at least one point that matches that average. In fact, this used to be used to give people speeding tickets. So for example, if you got on a road at a starting point and you got off at a different point there that it was like a toll road, they'd give you a little paper when you got on that said the time that you entered the last like little toll booth, and then the time that you got off later, and they compared them. And if you actually got there faster than the speed limit allowed, they'd immediately write you a ticket for speeding. But what speed would they give you for it? And the answer is they'd give you a ticket for your average speed. So if, say, it was the speed limit was 60 miles, and 60 miles per hour, and you went, you drove on it and went 60 miles, but you did it in only 45 minutes, then suddenly they know you had to have been speeding, and then they could justify giving you a ticket for your average speed because at some point during that trip, since your car has to change speeds continuously, and if we graphed it out, it would be a differentiable graph, that at some point during that entire trip, you at least one point had to have been going your average speed. So I don't know if they still do that. I know there was a lot of uproar over it, but yeah, that was the basic argument, is we could give you a ticket for that because we know you had to have at least at one point gone your average. So let's look at this. Assuming the function is continuous, on a closed interval AB and differentiable on the intervals interior AB, then between x equals a and x equals b, the curve has a tangent line parallel to the chord AB. So this chord is this right here. This is AB. That's this right there, connecting them straight. And then this parallel to it part, this parallel line, is this one right there. Okay? All right, so the secant slope will be equal to the tangent slope. At some point x equals c. And I guess I can color code these two as well. So the secant is the, what did I make that? I did this color for the secant. This is the secant, right? And this is the tangent. Okay? All right, so let's take a look at example 1. Find the values, find the location of the tangent line. So find the values of C that satisfy this equation, f of A minus f of B over B minus A equals f prime of C, in the conclusion of the mean value theorem. So in other words, we want to take the average slope between those 2 points and then find the point in the point or points in the interval in between those 2 points in the interval 7, 13, right, 7 to 13, that fit that. So in other words, what we're saying is this is A, this is B, okay? This is A, that B, okay? So let's try this. So let's talk about the actual average. The average slope between those 2 points is essentially, we're taking those 2 points, we're doing rise over run, so we need change in y over change in x, and that's what this equation right here does. It tells us essentially this is y2, this is y1, this is x2 and x1, right? So in other words, y2 is f of b, x2 is b, y1 is f of a, x1 is a. And so that's all this formula is doing. It's just doing our change in y over change in x, so the slope. So the slope average is going to be y2, which is f of b, minus y1, which is f of a, all divided by x2b minus x1a. All right, that's all it is, change in slope. And if we go ahead and start plugging in here, we have the natural log of 13 minus 6 minus the natural log of 7 minus 6 all over 13 minus 7. This brings this down here. This is going to equal the natural log of 7 minus the natural log of 1 over 13 minus 7 is 6. And if you should know this one, this is natural log of 1. So like, what does the natural log of 1 equal? So if you can't remember what this one is, remember natural log is base e, so it's a log base e of 1. And so you're kind of asking yourself, e to the what power equals 1? That's going to be 0. The other way you could think about this, other than just thinking e to the what power equals 1, kind of memorizing, is to, simply undo it. So e to the natural log of 1 equals e to our question mark. E to the natural log of 1 is just 1, and so we have e to the what equals 1, and again, it's got to be 0. So this is just a 0, that's gone. All right, so what we end up with is the average slope is just natural log of 7 over 6, okay? So now what we want to do is take a look at the derivative function and find everywhere that it actually equals that. So let's take the derivative of this function. So f prime of x is going to be the derivative of the natural log, so we're chain ruling it here. We have to do the derivative of the outer function, which is the natural log. That's 1 over what's on the inside times the derivative of what's on the inside. Well, the derivative of x is 1, and the derivative of 6 is 0. So that's it right there. It's just 1 over x minus 6. There's our derivative function. Now we want to set that equal to the average. So this means what we'll have is 1 over x minus 6 equals natural log of 7 over 6. And we just have to solve then for what x is. So first thing we can do is take the reciprocal of both sides. That gives us x minus 6 on the left. Really, it's x minus 6 over 1, but we don't usually write over 1. and this becomes 6 over the natural log of 7. And then I just add 6 to both sides. This becomes 6 over the natural log of 7 plus 6. And then that is our actual C value that we're looking for, where it turns out to be. And if you type this into a calculator, so in other words, this is our value for C right here. And if you type this into a calculator, you will find that it is that it is greater than 7. Type it into a calculator, see what value you get. You can find it's greater than 7 and less than 13. So it is actually in that interval if you try it. Okay? The next one I'm going to leave for you to try. So you try and then take a look in the notes where I will have solved it. You're doing the same thing. Find the average between 2 and 5, the slope that connects those 2 points for that graph, and then find all of the points, might be one, might be more, that actually then satisfy and have that slope. If this is a smooth and continuous graph, you're going to find at least one. Next, there was an example here. I don't really like it very much. So instead, what you should do is go see this example in the book. Okay, go see this example instead. I think that's a better example. So go see that example. Okay, and yeah, it's all worked out for you there, so I'm not going to work it out in the notes. But if you have any questions on it, just let me know. So now let's talk about answering these questions that we posed at the beginning. So we know that any constant function has a derivative of 0, but could there be a more complicated function whose derivative is always 0? So our corollary 1, if f prime of x equals 0, then f of x equals c. So basically we're saying no. If it is if the derivative is always 0, then it has to be a constant function. And so why? Why is that the case? Because if we have f of b minus f of a over b minus a equal to 0, then we can multiply both sides by b minus a, right? So by what's on the bottom, b minus a times b minus a. And so that cancels there, and it goes to 0 on the right-hand side. So then we end up with f of b minus f of a equals 0. And if that's the case, then f of b equals f of a, which means so for any points we pick, this is true for all, that's a for, not a far, for all a and b. And therefore, if they're always equal to each other, no matter what 2 points you pick, this means it's a constant. All right, so we can't have anything else that is like that. So if the derivative is equal to 0, then your original function is a constant function, not the constant function. It might be x equals 7, or I'm sorry, y equals 7, or y equals 100, or y equals 1,000,000. All right, let's take a look here. If two functions have identical derivatives over an interval, how are the functions related? And so here's our corollary 2. If f prime of x equals g prime of x at each point x in an open interval, a, b, then there exists a constant, we'll call it c, such that f of x equals g of x plus that constant for all x in the element of ab, so for all x in that interval. So if you think about this, this should make sense. If you do the derivative of f of x, you get f prime of x. If you do the derivative of g of x plus c, you get g prime of x, right? And then the c part just goes to 0. So if these two then equal each other, then the two previous have to equal each other. That means f and g are the same. They're just off by a constant. Okay? And so you can see that in this picture over here. You can see we have a whole bunch of curves that if we went through and started drawing in tangent lines to them at the same location, so like say we picked this vertical line right here, every tangent line we draw in, they're all going to be parallel. So if we do the derivative function of each one of them, and then we go to the same x coordinate for each one, they're all going to turn out to be the same because the constants that caused, in other words, these constants here, they do vertical shifts like that. That constant added off to the side like that, they vertically shift your graph, which doesn't affect the slope at all. It just shifts it vertically. All right. So if you want to think of it that way, that's the way I think of it. So geometrically, this says that the graphs of functions with identical derivatives on an interval can only differ by a constant. And it's because that constant goes to 0 when you take the derivative. So you end up with the same function once you take the derivative. The graphs to the right are functions that all have a derivative of 2x because they're all x squared plus something. So when you take that derivative, this x squared becomes 2x, and this becomes 0. And so every single one of them has that same derivative, 2x. All right, let's take a look at another example. Here, thinking backwards, I'm gonna do a little bit of these for you, but then I'm gonna want you to work on some of these. So I might do 2 of these here. So find the function f for the given derivative and whose graph passes through the point P. So this is an important skill when we start getting into antiderivatives, but we're basically starting off where we have the derivative and we have to figure out what the original function was. All right, so we look at this, we know the derivative is sine of x, and we think, well, the derivative of what gives us a sine of x? Well, a derivative of cosine of x is going to equal negative sine x, we know that. So maybe if instead we did the derivative of the negative cosine of x, that then gives us the derivative of sine of x. So immediately we find that f of x is equal to negative cosine of x. If we take that derivative, if we take the derivative of this, we will get this up here. All right? So you had to think a little bit backwards. We could be a little more general because, as we just saw in our previous page, anything with that's differed by the addition of a constant gives us the same derivative function. So in fact, we could say f of x equals negative cosine x plus some constant that may or may not be there. It might be a 0, it might be a 1, it might be 100, but there might be there. And when I take this derivative, this part's going to give me sine of x, this part's going to give me 0. So it's going to go away. All right? So we have to always, whenever we're working backwards, we pretty much always have to wonder, is there that plus c there? And so now we have to find when does it pass through the point 0, 2. So now we just plug in 0, 2 to find c. So we have negative cosine of x, so that's a 0, plus c, and it has to equal 2 because that's what it is. This is x, this is y, all right? And f of x is just y. So it has to equal 2. That means that when we do this, we got cosine of 0, which is 1. So this is negative 1 plus c equals 2. And so c then ends up equaling 3. And so our final answer for what gives us, what function gives us this derivative and passes through this point is f of x equals negative cosine of x plus 3. And there's our final answer. All right? And I'm going to leave this next one for you to try, but you can take a look in the notes and see what the answer is. So let's take a look at this next one down here then. And I'll do one of these, and again, I'll leave the next one for you. Find all possible functions with the given derivative. So here, we're doing something kind of similar. We're asking ourselves the derivative of what gives us 3 times e to the 4x. So the key here in this one is to look at the e to the 4x. What happens? What's the derivative of e to the 4x? All right? What is that? Well, it's going to be e to the 4x times 4. So if we have an e to the 4x in our derivative, that means we must have started with an e to the 4x at the beginning of our function before we took the derivative. The only difference is we ended up with this 4 here, and up here we have this 3. So how do we turn a 4 into a 3? And the answer is, what can we do to this to make it that? So in other words, how do we make 4e to the 4x equal 3e to the 4x? Like, how do we do that? And the answer is we're going to have to multiply it by something. And in fact, if we multiply it by 3/4, then they suddenly equal each other, right? So in other words, what is the derivative of 3/4 e to the 4x? And the answer is you carry that 3/4 along. You do the derivative of e to the 4x, which we just did right here, which is 4e to the 4x. And then the 4 cancel with the 4, and we're left with 3 times e to the 4x. All right, and so that tells us then f of x is equal to 3/4 e to the 4x, just like that. And then that is our original function. The only thing is, what if there had been a constant? Well, we don't know. There might have been a constant, so we'll put a plus c here. This is all the possible functions with that given derivative. Okay? So now we have that. If we do the derivative of that, we're going to get, always end up getting back to this right here, and it doesn't matter what constant we add on to it. So we basically have all the possible ones. This could be 3/4 e to the 4x plus 1, plus 2, plus 100, plus 1,000,000, minus 70, anything we want for that c, and that'll work. So there's our answer. So I'm going to leave this next one for you to try, where you're going to think to yourself, the derivative of what will give me 1, and the derivative of what will give me 1 over x squared. So you kind of have to do some thinking backwards through the process of taking derivatives. We're doing them in reverse now. All right, so let's take a little look here at an introduction to initial value problems. So an object is falling freely from rest with an acceleration of, we're going to make this negative 9.8 meters per second squared, and that is actually the free fall acceleration near Earth's surface. And we're going to want to try and go through and do this. Now, to make this a little similar, I'm going to set that equal to g, just like it would be in a physics class. G is going to represent negative 9.8 meters per second squared. And just to make that a little more clear, I'm going to write g equals negative 9.8 meters per second squared. There we go. That's free fall acceleration near Earth's surface. So let's start with A. Find the velocity function. So, and it's falling from rest. So this is our hint. We're assuming it falls from rest. So remember that acceleration is equal to the rate of change of velocity, so dv dt. So if we have a velocity function and we take the derivative of it, we get the acceleration function. Well, we're already told that the acceleration function is a constant. So acceleration equals a constant g right there. And according to what we have above, that means that this is actually the derivative of the velocity function, dv dt. So we have to ask ourselves, the derivative of what will give us just this constant g, which represents our 9.8 or negative 9.8 meters per second squared. And so we got to work backwards. And so the first one is that, oh, that needs to go away, is that we say v as a function of time. So before we took the derivative, we had to have something, the derivative of what gives us a constant with respect to time. Well, that's just g times t, like just x. The derivative of x is 1. So the derivative of like 8x is just 8, right? d dx. And so d dt of 8t is 8, right? The derivative of whatever the constant is, you carry it along there. So that's what we're doing here. And then we have to include some sort of constant. In this case, the constant has to be a velocity, because you can't add on to a velocity something it isn't a velocity. You can't say something like, what's 5 miles per hour plus 2 pounds? So if we're adding something on, it also has to be a velocity. We're going to represent it with v naught and call it the initial velocity. But if you remember, we had an initial value which says that it started from rest here, which says that our initial velocity, whatever it is, in other words, whatever v at 0 time is, has to equal 0. That means that gt, well, not gt, g times 0 plus v naught has to equal 0, because we said it equaled 0 right there, right? And so this g times 0, that means that our initial velocity also has to equal 0, which means it's gone, which means we happen to have the case where our vertical shift is nothing, and that's our final answer. V as a function of t is just gt, and if you wanted to, I guess you could put back in the negative 9.8 meters per second squared for the for the g. So either one of those, probably fine, but you should get used to working with variables instead of numbers. All right, so part B simply asks us to now find the position function. All right, so find its position at time t, so that's a position function. And remember that, that velocity is the rate of change of position. It's the slope of the position function. So it means we need to take this again, our previous result, and try to do the reverse derivative of it to get whatever we took the derivative of that gave us that. So s of t has to equal, and we have to work backwards from our velocity function. So using this right here, or actually better yet, using this one right here, we ask ourselves the derivative of what gives gt. Well, look at this. It's going to be 1/2 gt squared. So if you think about this, I take the derivative, that 2 is going to come out front and going to cancel with the 1/2, and then that 2 is going to become a 1, and I'll be left with just a g times t. So that right there works. And then I have to add on a constant. And in this case, it has to be a position constant, so s naught, which again should be our initial position, which it tells us up here, since it falls from rest, not really, but we're starting at 0, right? If you're going to measure something, that shouldn't be there. If you're going to measure something, you need to, you always line up the 0 of your ruler. You don't, just slap it down randomly and start measuring the distance. You got to line it up. So in other words, what we're saying is s of 0 equals 0. We're starting from our origin. And so then that means that this is 1/2 g times 0 squared plus s naught. This is 0 squared, that whole thing's a 0. And then that means that s naught just equals 0. And so our final function for position in this case is gt squared, is just this. Now, not every problem is going to have those go to 0, but it might. They usually try to set it up where you get as much stuff to be 0 as you can, but not always. And then part C, I want you to think about what if A, the acceleration, is a function of time, not just 0, or not just a constant. I mean, not 0. 0 would be a constant too, but then nothing's happening really. But what if it's not just a constant? What if it's a function? Like, that was supposed to be a k, like 2t squared, or the cosine of 10t, or something like that. Like, what happens if the acceleration is one of these things? And I want you to think, what then would my velocity function look like, and what would my position functions look like if you could do that? All right, so just spend a little time thinking about that, because it doesn't always have to be a constant. We may not have a constant acceleration in a certain situation. All right, that's pretty much it for this. Be sure to do those couple that I left blank for you and check back in the notes to see the answers. All right, that's it. Thanks.